The summer sun burned white over Sardinia's coastal airfield at Capoterra, June 12, 1943. Ground crews watched a twin-boomed silhouette descend through the Mediterranean haze, its distinctive form unmistakable even at a distance. The Lockheed P-38 Lightning touched down smoothly on Italian soil, its American star still visible beneath a thin coating of dust. The pilot climbed from his cockpit, disoriented, reaching for his compass. 30 degrees off course, a navigation error that would rewrite what Axis engineers believed possible about American aviation technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within hours, Colonel Angelo Tondi, chief test pilot for the Regia Aeronautica's experimental center at Guidonia, received urgent orders. An intact American fighter awaited him in Sardinia, not damaged, not compromised by combat, fully operational, with every system functioning exactly as American engineers had intended. The Lightning represented something German and Italian aviation had pursued for years but never quite achieved: a twin-engine fighter that could match single-engine performance while delivering range and firepower impossible in conventional designs. As Tondi flew the captured aircraft northeast toward Rome, every kilometer revealed capabilities that challenged fundamental assumptions about what twin-engine fighters could accomplish. German intelligence officers had tracked P-38 deployments across North Africa and the Mediterranean with growing concern. Reports described an aircraft that climbed rapidly to altitudes where Axis fighters struggled. Pilots spoke of concentrated nose-mounted firepower that didn't require convergence calculations. Range estimates suggested operational radii that exceeded anything German twin-engine designs could match. But seeing the physical aircraft, testing its systems, measuring its actual performance that would reveal truths numbers on paper never could. The captured Lightning was transported to Rechlin, Germany's premier aviation testing facility, where Luftwaffe engineers prepared evaluation protocols that would expose either American brilliance or American propaganda. The story of this single captured aircraft would trigger a crisis of confidence among German aviation engineers that would echo through their fighter development programs for the remainder of the war. The mathematics of twin-engine fighter design were about to be rewritten, not through superior firepower or armor thickness, but through turbo-supercharger technology and automotive engineering principles Germany had never successfully mastered. Rechlin Proving Ground, Brandenburg, Germany. July 1943. The captured P-38 Lightning bore fresh German markings as it rolled across the tarmac toward the main testing hangar. Test pilots and engineers gathered with notebooks, cameras, and measuring instruments, documenting every detail of this prize from the Mediterranean theater. The Luftwaffe testing center at Rechlin, located approximately 100 kilometers northwest of Berlin, served as Germany's primary evaluation facility for both German and captured Allied equipment. Here, methodical engineers measured, tested, and analyzed everything from control surface deflection to fuel consumption rates, documenting their findings in exhaustive technical reports that circulated through Wehrmacht technical branches and the Reich Air Ministry. The P-38 Lightning represented the culmination of American pursuit of twin-engine fighter design philosophy fundamentally different from German approaches. Where Germany built twin-engine fighters as tactical compromises, accepting reduced maneuverability for increased range and firepower, American designers at Lockheed had pursued something more ambitious, a twin-engine aircraft that wouldn't compromise fighter performance. German twin-engine fighter development had followed a predictable path. The Messerschmitt Bf 1-10, introduced in 1937, embodied Hermann Göring's vision of a heavily armed Zerstörer destroyer that would escort bombers deep into enemy territory and sweep opposing fighters from the sky. Early prototypes achieved speeds exceeding 500 km per hour, faster than contemporary Bf 109 single-engine fighters. The Bf 1-10's maximum speed of approximately 336 miles per hour impressed Luftwaffe leadership initially. Twin Daimler-Benz DB601 engines provided adequate power. Armament proved devastating, 4 7.92 mm machine guns plus two 20 mm cannons in the nose, supplemented by a defensive machine gun for the radio operator. Range exceeded single-engine fighters by substantial margins, but combat revealed fatal limitations. The Battle of Britain exposed the Bf-1-10's poor maneuverability. British Spitfires and Hurricanes, lighter and more agile, slaughtered German Zerstörer formations. On August 15, 1940, nearly 30 Bf-110s fell in a single day. Losses mounted so rapidly that Goering ordered the type withdrawn from daylight escort duties after just months of operations. The Messerschmitt Me 2-10, developed as a Bf-1-10 replacement, encountered even worse problems. Design flaws caused catastrophic handling characteristics. Test pilots reported the aircraft snaked through the air unpredictably. Stalls whipped into uncontrollable spins. The second prototype crashed when its pilot couldn't recover from a spin, killing him. 16 prototypes and 94 pre-production examples attempted to resolve the problems. Nothing worked. Yet the Reich Air Ministry, desperate to replace aging Bf-110s, ordered full production anyway in early 1941. The predictable disaster forced continued reliance on the obsolete Bf-1-10 design. The Me 4-10, a substantially redesigned Me 2-10 variant, finally achieved acceptable flight characteristics by 1944. Maximum speed reached approximately 390 miles per hour, 50 mph, faster than the Bf-1-10. But by then, Allied air superiority rendered any German twin-engine dayfighter increasingly vulnerable to swarms of P-51 Mustangs and P-47 Thunderbolts. German engineers understood twin-engine fighter theory perfectly well. They possessed extensive scientific knowledge and sophisticated aerodynamic understanding. What they lacked was the specific technological solution that made the American P-38 fundamentally different: turbo-supercharger technology that maintained engine power at high altitudes where German engines gasped for oxygen. The P-38's development began with a February 1937 specification from the United States Army Air Corps. Requirements seemed impossible: achieve 360 mph at 20,000 feet, climb to that altitude in 6 minutes, carry heavy armament, and operate at long range. Contemporary single-engine designs couldn't meet those parameters. Kelly Johnson, a 27-year-old engineer at Lockheed, calculated that only a twin-engine configuration could generate sufficient power while maintaining the required speed and altitude performance. Johnson's radical design featured twin booms housing Allison V-17-10 liquid-cooled engines, with the pilot seated in a central nacelle. This configuration allowed nose-mounted armament 450 caliber machine guns, plus one 20 mm cannon that fired in parallel streams without requiring convergence adjustments. The critical innovation appeared deceptively simple: turbo-superchargers mounted atop each engine nacelle. These exhaust-driven compressors forced additional air into the engines at high altitude, maintaining sea-level power output where normally aspirated engines lost 70% of their capability. Turbo-supercharger technology had existed since World War I, but American engineers at General Electric had refined it into a practical, reliable system during the 1920s and 30s. The technology required substantial development. Exhaust temperatures exceeded 1,000 degrees Fahrenheit. Bearing materials had to withstand extreme thermal stress. Control systems needed precise regulation. German engineers had experimented with turbo-superchargers, but abandoned the effort due to manufacturing difficulties. The BMW 801T engine, tested in limited numbers aboard Ju-88 reconnaissance aircraft, represented Germany's only operational turbo-supercharged power plant. Complexity exceeded German industrial capacity during wartime conditions. American industry, by contrast, had mature automotive and aviation sectors, with decades of experience in mass-producing complex mechanical systems. General Electric supplied turbo-superchargers for B-17 bombers, B-24 bombers, and P-38 fighters by the thousands, achieving remarkable consistency and reliability. The XP-38 prototype first flew in January 1939. Test pilot Lieutenant Ben Kelsey immediately recognized extraordinary potential. On February 11th, he attempted a transcontinental speed record, covering the distance from California to New York in 7 hours and 48 minutes, then crashed on approach to Mitchell Field due to carburetor icing. Despite the crash, performance data proved the design sound. Development continued through numerous variants addressing specific operational challenges. Early models suffered compressibility problems in high-speed dives. Shock waves forming over wings made elevators uncontrollable. Engineers developed electrically powered dive flaps that disrupted the shock waves, solving the problem by late 1944. Counter-rotating propellers eliminated torque, effects that plagued single-engine fighters. Tricycle landing gear provided excellent ground handling. The distinctive twin-boom configuration proved aerodynamically efficient while providing structural strength and ample internal volume for fuel, equipment, and turbo-supercharger installations. By June 1943, when the P-38G landed at Capoterra, the Lightning had evolved into a mature, capable weapons system. Maximum speed approached 420 miles per hour at 25,000 feet. The service ceiling exceeded 44,000 feet. Combat radius with drop tanks reached 700 miles. Firepower concentrated in the nose proved devastating against lightly armored Japanese aircraft and effective against German fighters. American pilots in the Pacific Theater praised the Lightning's long-range capability, heavy armament, and high-altitude performance. General George Kenney, commanding 5th Air Force, specifically requested P-38s because their range allowed operations across vast ocean distances where engine failure meant certain death. Twin engines provided redundancy that saved countless lives when battle damage or mechanical problems disabled one power plant. The captured Lightning at Rechlin represented more than just an enemy aircraft. It embodied American industrial maturity, technological sophistication, and engineering philosophy that prioritized practical functionality over theoretical optimization. German test pilots and engineers were about to discover how far American aviation had advanced beyond their own capabilities. Summer 1943, Rechlin Proving Ground. German test engineers conducted the initial inspection of the captured P-38 with teams of specialists from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, and documented construction techniques that seemed remarkably straightforward compared to German methods. The turbo-supercharger installations caught immediate attention from power plant specialists. Each Allison V1710 engine sat in its nacelle, with the turbo-supercharger mounted directly above, integrated into the engine boom structure. Exhaust piping routed hot gases from the engine to the turbine wheel. The compressor section drew ambient air, compressed it, and fed it through an intercooler before delivering it to the engine's intake manifold. Hans-Werner Lersch, Rechlin's principal test pilot, examined the installation with particular interest. Lersch had flown over 120 different aircraft types during his career, including numerous captured Allied designs. The P-38's turbo-supercharger system represented technology Germany had attempted but never successfully implemented in operational fighter aircraft. German engineers noted the substantial weight and complexity of the turbo-supercharger installation. The system added approximately 200 pounds per engine weight that reduced theoretical performance. American designers had accepted this penalty because the altitude performance gains justified the mass increase. At 25,000 feet, where German fighters struggled with reduced power, the P-38 maintained near sea-level performance. The intercooler system revealed additional American sophistication. Compressed air heated significantly during compression basic thermodynamics. Without cooling, this hot compressed air reduced effective power output. The Lightning's intercoolers, mounted in the leading edges of the center wing section, cooled the compressed air before it entered the engine, substantially increasing power output at altitude. German Bf 1-10 and Me 4-10 fighters used mechanically driven superchargers compressors geared directly to the engine crankshaft. This approach proved simpler and lighter than turbo superchargers but suffered fundamental limitations. Mechanical superchargers consumed engine power to drive the compressor, reducing net power output. At high altitudes, where maximum boost was needed, the supercharger consumed 20 to 30% of engine output just to compress incoming air. Turbo superchargers, by contrast, extracted energy from otherwise wasted exhaust gases. The turbine wheel spun at extreme speeds, often exceeding 50,000 RPM, driven entirely by exhaust flow. This free energy source meant the compressor added boost pressure without consuming crankshaft power. Net result: substantially higher effective power output at altitude compared to mechanical supercharging. The examination revealed additional design details that impressed German engineers. The Lightning's counter-rotating propellers eliminated asymmetric torque effects entirely. German twin-engine fighters used engines rotating in the same direction, creating handling challenges during single-engine operations. American engineers had specified one right-hand and one left-hand engine, ensuring torque forces were cancelled perfectly. Fuel system design demonstrated American emphasis on operational range. Internal tankage totaled 410 gallons, substantially more than German fighters. Provisions for external drop tanks allowed carrying an additional 320 gallons, bringing total capacity to 730 gallons. This enormous fuel load enabled combat radii exceeding 1,000 miles when required. The hydraulic system operating flaps, landing gear, and dive brakes proved remarkably reliable. German aircraft increasingly suffered hydraulic failures as strategic bombing disrupted production of high-quality seals and fittings. The American system used components proven in commercial aviation applications, manufactured to tolerances that ensured consistent performance even under combat conditions. Electrical systems showed similar maturity. The P-38 featured redundant generators, one driven by each engine. If one engine failed, the remaining generator supplied all electrical loads. Turret traverse for the guns continued operating even if the primary electrical system failed, powered by a backup generator. German fighters lacked such redundancy, accepting that electrical failures would disable critical systems. Construction techniques revealed American mass production expertise. Flush riveting reduced drag while simplifying manufacturing. Interchangeable components meant field repairs required no custom fitting or adjustment. Tolerances that would be considered sloppy in German precision manufacturing resulted in aircraft that functioned reliably under field conditions. German manufacturing emphasized tight tolerances and perfect fits craftsmanship that looked impressive but proved counterproductive for wartime mass production. American engineers designed for ease of manufacture, accepting looser tolerances that actually improved reliability by reducing binding and friction in operating mechanisms. The instrument panel layout reflected American pilot training philosophy. Controls and instruments followed standardized positions, familiar to any pilot trained in American aircraft. Throttle quadrant placement, mixture controls, propeller pitch controls, all positioned identically to civilian aircraft and other military types. German fighters featured unique layouts requiring extensive type-specific training. After weeks of static examination, engineers prepared for flight testing. The Lightning had been flown only briefly since capture Italian pilots ferried it to Guidonia, then German pilots flew it to Rechlin. Comprehensive performance testing would reveal whether American claims about altitude performance and speed matched reality. Lersch drew the assignment to conduct initial flight evaluation. His experience with captured aircraft made him the logical choice for this critical assessment. On a clear summer morning, he climbed into the Lightning's cockpit, settled into the comfortable seat, and began the startup sequence. The twin Allison engines fired smoothly, their distinctive sound different from the sharper note of German inline engines. Lerche advanced throttles carefully, monitoring instruments as a turbo supercharger boost built. The controls felt responsive, the tricycle landing gear providing excellent visibility during taxi. Takeoff revealed the P-38's docile handling. The aircraft lifted smoothly at approximately 105 miles per hour. Gear retraction proceeded without complications, and the climb performance impressed immediately. At full military power, the Lightning ascended at approximately 4,500 feet per minute, substantially better than any German twin-engine fighter Lersch had flown. Altitude performance proved even more remarkable. At 20,000 feet, where German fighters noticeably lost power, the Lightning's engines maintained strong output. The turbo-superchargers were doing exactly what American designers had intended, compressing thin air at altitude to maintain sea-level power density. At 25,000 feet, the difference became unmistakable. Bf 1-10 fighters at this altitude struggled with reduced power, sluggish acceleration, and compromised climb rate. The P-38 felt almost as powerful as at sea level. Lersch could maintain 400 miles per hour indicated airspeed with reasonable throttle settings. The service ceiling, the altitude where climb rate dropped to 100 feet per minute, exceeded 44,000 feet. German intelligence reports had suggested P-38s operated effectively at altitudes where Luftwaffe fighters couldn't follow. Flight testing confirmed this. At 30,000 feet, the Lightning maintained performance that would allow it to dictate combat engagement terms. German fighters reaching that altitude barely had energy to maneuver. Speed testing revealed maximum velocity approaching 420 mph at optimal altitude. This matched or exceeded the latest German single-engine fighters and substantially exceeded any German twin-engine fighter. The Bf 1-10C variant managed approximately 336 miles per hour maximum speed. The Mi 4-10 reached approximately 390 miles per hour. The Lightning achieved these speeds at higher altitudes where German engines couldn't maintain equivalent power. Handling characteristics proved surprisingly pleasant. The Lightning wasn't as nimble as single-engine fighters, its size and weight prevented that, but it responded predictably to control inputs. Roll rate, initially sluggish in early models, had been improved through power-assisted ailerons. The aircraft felt stable in all flight regimes, inspiring confidence rather than demanding constant attention. Dive testing revealed both strengths and limitations. The Lightning accelerated rapidly in dives, reaching speeds where compressibility effects appeared. Without dive flaps, the captured aircraft was a G model, predating that modification shock waves formed over the wings at high indicated airspeeds, causing control stiffening. Pilots had to anticipate this and begin recovery earlier than in conventional fighters. But even with this limitation, dive performance exceeded German expectations. The Lightning's structural strength allowed sustained high-speed flight that would damage lighter aircraft. Lersch pushed the aircraft to its limits, documenting buffeting onset, control force requirements, and recovery characteristics. The data revealed an aircraft engineered with substantial safety margins. Fuel consumption measurements during extended flights showed remarkable efficiency at cruise settings. The engines, operating with turbo-supercharger boost carefully managed, consumed fuel at rates that enabled the reported combat radii. German intelligence had suspected American range claims were exaggerated. Testing proved they were conservative. The concentrated nose armament demonstrated during gunnery trials proved devastating. 4 50-caliber machine guns plus 120 mm cannon, all firing through the propeller arc with no convergence required, delivered firepower along a precise line extending directly ahead. German fighters with wing-mounted guns had to calculate convergence the distance where bullet streams from left and right wings intersected. The Lightning's nose guns simply pointed wherever the aircraft pointed. The rate of fire exceeded 4,000 rounds per minute combined. The 20 mm cannon fired approximately 650 rounds per minute. The 50 caliber guns each fired approximately 850 rounds per minute. This concentration of firepower, aimed with precision, proved lethal against any target within 1,000 yards. German test pilots who flew the Lightning universally praised certain characteristics while noting others. The altitude performance impressed everyone. The long range seemed almost wasteful given German operational requirements. Luftwaffe fighters rarely needed to operate more than a few hundred kilometers from their bases. The firepower concentration was acknowledged as superior to wing-mounted arrangements, but the size bothered them. The Lightning weighed over 17,000 pounds, loaded substantially more than German fighters. Its wingspan exceeded 52 feet. This bulk made it visible from great distances, eliminating surprise, a critical tactical advantage. Its large size also meant German pilots could identify it immediately, often choosing to avoid combat with escorted bombers when Lightnings provided protection. The tricycle landing gear drew mixed reactions. German pilots trained on conventional tailwheel aircraft found the nosewheel arrangement unfamiliar initially, but they quickly recognized advantages: better visibility during taxi and takeoff, easier ground handling, reduced risk of ground loops. American pilots with minimal training could operate Lightnings safely. German pilot training emphasized skills necessary to handle more difficult conventional gear arrangements. Maintenance examination revealed American design philosophy that prioritized field serviceability. Access panels provided clear paths to components requiring regular attention. Engine removal and installation required no special tooling. Turbosuperchargers, while complex, could be replaced as complete units rather than requiring in-situ repairs. German aircraft increasingly suffered from deteriorating manufacturing quality as the war progressed. Strategic bombing targeted critical production bottlenecks. Slave labor introduced deliberate sabotage. The Lightning, built in American factories far from any combat zone by motivated workers earning good wages, showed manufacturing quality that German factories hadn't achieved since 1941. By autumn 1943, Rechlin had accumulated sufficient data to produce comprehensive internal reports that circulated through Wehrmacht technical branches and Reich Air Ministry officials. The documents, intended for senior Luftwaffe officers and Armaments Ministry leadership, painted a sobering picture of comparative capabilities. The P-38 demonstrated American turbo-supercharger technology maturity that Germany fundamentally lacked despite theoretical knowledge and scientific expertise. Mass production techniques allowed manufacture in quantities Germany couldn't match while maintaining quality standards that German factories could no longer achieve. The entire design philosophy prioritized operational effectiveness rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. While German engineers methodically tested the captured Lightning at Rechlin, Italian test pilot Colonel Angelo Tondi prepared the aircraft that had landed at Capoterra for combat evaluation. Italian fuel proved too corrosive for the Lightning's tanks. American aviation gasoline had different chemical properties limiting flight time. But Tondi was determined to test the fighter's capabilities against its former comrades. August 11th, 1943, 1100 hours. Tondi took off from Guidonia in the captured P-38, accompanied by a Macchi C-205 Veltro fighter flown by Captain Franco Bonato. Radar stations reported approximately 50 American B-17 flying fortresses returning from bombing the railroad yards at Terni in Umbria. The Lightning's distinctive silhouette allowed Tondi to approach the bomber formation without immediate challenge. American gunners, seeing the familiar twin-boom shape, hesitated those critical few seconds before recognizing the Italian markings. By then, Tondi had closed to firing range. The concentrated firepower proved as devastating as German tests had predicted. Tondi's first burst struck B-17F serial number 42-3307, commanded by Lieutenant Joseph Geipel. The bomber, nicknamed Bonnie Sue, staggered under the impact. Fire erupted from one engine. The aircraft fell from formation as 6 crewmen bailed out. The fortress crashed into the Mediterranean off Torvajanica near Rome. Tondi pressed his attack, damaging a second B-17, serial number 42-30093, severely enough to force an emergency landing in the Tunisian desert, approximately 10 kilometers east of Saint-Donat. The crew survived but lost their aircraft. This single combat sortie demonstrated what German and Italian engineers had discovered through testing. The P-38 could be devastatingly effective when flown by experienced pilots under favorable conditions. The high-altitude performance, concentrated firepower, and speed advantage allowed Tondi to attack and escape before American escort fighters could intervene. But it was also the Lightning's final combat mission in Italian service. The corrosive fuel issue couldn't be resolved. Spare parts didn't exist. American aviation gasoline chemistry differed fundamentally from Italian and German fuel specifications. Within days, the aircraft was grounded permanently. The brief combat demonstration had proven the point German testing had already established. American twin-engine fighter design had achieved performance levels. Axis powers couldn't match with their current technology and industrial capacity. The fundamental technology gap centered on turbo-supercharger development and implementation. German engineers understood the theory perfectly. Exhaust-driven turbines spinning compressor wheels to force additional air into engines at altitude. The physics were straightforward. German universities taught the principles. German scientists published papers on thermodynamic efficiency and compressor aerodynamics. But understanding theory and implementing practical, reliable hardware proved entirely different challenges. Turbo-supercharger development required solving numerous engineering problems simultaneously. Turbine wheels had to withstand extreme temperatures and rotational speeds while maintaining precise balance. Bearings needed special materials and lubrication systems that functioned at temperatures exceeding 1,000 degrees Fahrenheit. Control systems must regulate boost pressure automatically across varying altitude and throttle conditions. General Electric had solved these problems through decades of methodical development work, funded initially by the United States Army Air Service during the 1920s. Early turbo-superchargers proved unreliable, suffering bearing failures and turbine wheel fractures. But American industry possessed the metallurgical expertise, precision manufacturing capability, and testing infrastructure to iterate through multiple design improvements. By 1940, when the P-38 entered production, General Electric turbo-superchargers had matured into reliable components that worked consistently across thousands of installations. American pilots flying B-17 bombers and P-38 fighters across the Pacific and European theaters depended daily on turbo-supercharger reliability. The systems rarely failed, despite operating in extreme environments, from tropical heat to Arctic cold, through battle damage and mechanical stress. German attempts at turbo-supercharger development encountered problems at every stage. Metallurgy proved inadequate, turbine wheels cracked under thermal stress, bearings seized from inadequate lubrication at operating temperatures. Control systems couldn't regulate boost pressure reliably, causing engine damage from overboost or power loss from insufficient boost. The BMW 801T engine, fitted to a limited number of Ju-88S reconnaissance aircraft, represented Germany's only operational turbo-supercharged power plant. Even this installation required compromises. The turbo-supercharger, engine, cowling, and intercooler were integrated into a single complex package that proved difficult to maintain and prone to problems. Production numbers remained minimal, a few dozen installations compared to thousands of American turbo-supercharged engines. German fighter development instead relied on mechanically driven superchargers with multiple speeds or variable gear ratios. The Daimler-Benz DB601 and DB605 engines used fluid coupling to vary supercharger drive ratios continuously, automatically adjusting boost based on altitude. This system worked reasonably well but consumed substantial engine power to drive the supercharger, limiting net power output at altitude. The Focke-Wulf 190 used a BMW 801 radial engine with a two-stage mechanical supercharger. This configuration provided good altitude performance up to approximately 25,000 feet, but suffered power loss above that altitude. Development work on a 3-speed or 4-speed supercharger continued throughout the war, but never reached operational status before Germany's defeat. Even if German engineers had solved the turbo-supercharger reliability problems, manufacturing capacity constraints would have prevented mass production. Turbo-superchargers required precision castings, special alloy turbine wheels, high-temperature bearings, and complex control mechanisms. German industry, stretched to breaking point supplying conventional weapons, couldn't absorb additional production complexity. Strategic bombing compounded these problems. Allied attacks targeted bottleneck facilities in the German production system with increasing effectiveness. The Maybach engine plant in Friedrichshafen suffered severe damage from a Royal Air Force Bomber Command raid on the night of April 27 to 28, 1944. The attack involved 322 aircraft and destroyed both the engine plant and the adjacent ZF gearbox factory. Production of tank engines and transmissions halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly. Similar attacks disrupted aircraft engine production, forcing increased reliance on slave labor that introduced deliberate sabotage into the manufacturing process. American industry faced no such constraints. Factories in Detroit, California, and other locations operated safely far from combat zones. Workers received good wages and worked under decent conditions, producing high-quality components consistently. The industrial infrastructure built during decades of automobile mass production translated directly into aviation component manufacturing capability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. General Electric alone produced tens of thousands of turbo superchargers during the war years. Multiple manufacturers built Allison V1710 engines. Lockheed, operating dedicated production facilities, manufactured over 10,000 P-38 aircraft in various models. This scale of production exceeded Germany's entire twin-engine fighter output combined. The comparison grew even more painful when examining operational readiness rates. German twin-engine fighters, particularly later models like the Me 4-10, suffered chronic mechanical problems. The complex systems required constant maintenance by highly trained specialists. Spare parts shortages meant aircraft sat grounded, awaiting components that never arrived. American P-38s, while not immune to mechanical issues, maintained substantially higher operational availability. The turbo supercharger system, though complex, proved reliable in service. Maintenance procedures, documented in clear manuals, allowed mechanics with basic training to perform most repairs. Spare parts flowed through supply chains that never broke down despite global distances. The captured Lightning at Rechlin represented more than just superior technology. It embodied an entire industrial and operational philosophy fundamentally different from German approaches. American designers built aircraft that mechanics with civilian automotive training could maintain using skills they already possessed. German designers built aircraft that required specialist training and constant expert attention from personnel with years of specific military technical education. This difference manifested in every aspect of Lightning operation. The Allison engines used conventional automotive-style maintenance procedures. Oil changes, spark plug replacement, valve adjustments all followed patterns familiar to anyone who had worked on automobile engines. German aircraft engines, while theoretically more sophisticated, required specialized knowledge and procedures that weren't transferable from civilian experience. The turbo supercharger system, while complex, was designed for field maintenance. The entire unit could be removed and replaced without disturbing the engine installation. German supercharger installations integrated tightly with the engine, requiring extensive disassembly for maintenance or repair. Electrical systems demonstrated similar philosophical differences. The P-38 used standard commercial-grade switches, circuit breakers, and wiring that could be sourced from multiple suppliers. German aircraft increasingly used proprietary components manufactured by specific suppliers, creating logistics nightmares when those suppliers suffered bomb damage. Even simple details revealed the difference. American pilots received heated flight suits powered by the aircraft's electrical system, allowing comfortable operation at extreme altitudes where temperatures dropped to -40 degrees or colder. German pilots relied on bulky electrically heated suits that often malfunctioned or simply endured the cold, which degraded combat effectiveness. The Lightning's cockpit heating system worked reliably, drawing engine heat through a simple exhaust shroud arrangement. German fighters suffered chronic heating problems, leaving pilots dangerously cold during high-altitude operations over the Reich. Cold pilots made mistakes, missed targets, and failed to maintain formation discipline. Range and endurance differences created operational advantages that multiplied across entire campaigns. A P-38 could escort bombers deep into enemy territory, engage defending fighters, and return to base with fuel reserves. German twin-engine fighters, limited by fuel capacity and consumption rates, couldn't match this operational flexibility. The Bf 1-10 had internal fuel capacity of approximately 540 gallons and range around 680 miles. The P-38 carried 410 gallons internally, but could carry 320 gallons in external tanks, bringing total capacity to 730 gallons. Combat radius exceeded 1,000 miles when required nearly double the German fighters' capability. This range advantage meant American fighters could strike targets German defenses couldn't adequately protect. Industrial facilities, airfields, transportation networks all became vulnerable to attacks from distances where German fighters couldn't intercept effectively. The cumulative effect degraded German military capability month after month. German fighter pilots who encountered P-38s learned to respect their capabilities while exploiting their weaknesses. The Lightning's size made it visible from great distances, eliminating surprise. Its limited low-altitude maneuverability meant German fighters could escape by diving away if caught at disadvantage. The recognition factor twin booms unmistakable even at long range allowed tactical decisions before engagement. But these minor advantages couldn't overcome the fundamental performance gap at altitude. When bomber formations approached at 25,000 feet or higher, escorted by P-38s operating in their optimal regime, German interceptors faced a nearly impossible tactical situation. Climbing to intercept altitude consumed fuel and energy. By the time German fighters reached bomber altitude, the P-38s had positional advantage and could dive on them at will. Adolf Galland, General of Fighters, assessed the P-38 dismissively in public statements, claiming it had similar shortcomings in combat to our Bf 1-10 and that German fighters were clearly superior to it. But private communications told different stories. Operational reports documented heavy losses among bomber formations the Lightnings escorted. Galland's public dismissal served propaganda purposes more than accurately reflecting combat reality. Kurt Bühligen, third highest scoring German pilot on the Western Front with 112 victories, offered a more honest assessment. The P-38 fighter and the B-24 were easy to burn. Once in Africa we were 6 and met 8 P-38s and shot down 7. But this victory occurred in Africa at low altitude, where the Lightning operated outside its optimal envelope. At high altitude over Germany, outcomes reversed dramatically. Franz Schiess, a German ace with 67 victories including 17 P-38s, became the Luftwaffe's leading Lightning killer. His success came primarily from tactical positioning and exploiting moments when American pilots made mistakes. Against well-flown Lightnings at altitude, even top German aces struggled. The fundamental problem for German twin-engine fighter development was that the P-38 solved problems Germany couldn't solve. Turbo supercharger reliability, high-altitude engine performance, long-range operational capability, mass production at scale. Every advantage American designers achieved came through industrial maturity and technological sophistication. Germany lacked access to during wartime conditions. Internal German intelligence assessments of the P-38, compiled from Rechlin testing data and combat reports, circulated through Luftwaffe headquarters with increasing urgency through late 1943 and 1944. The documents, classified as secret, revealed stark truths about American aviation capabilities. Performance data confirmed the Lightning could operate effectively at altitudes where German fighters struggled. The turbo supercharger system maintained power output to 44,000 feet, well beyond the effective ceiling of Bf 109s or FW190s. This altitude advantage allowed American pilots to control engagement terms, fight when advantageous, disengage when threatened. Range calculations showed the P-38 could escort bomber formations to targets throughout Germany and occupied territories, while German fighters operated under severe fuel constraints. The implications for bomber defense became clear. No target in the Reich lay beyond range of American escort fighters. Firepower concentration assessments noted the nose-mounted armament's deadly accuracy. German fighters with wing-mounted guns required complex lead calculations and convergence considerations. The Lightning pilot simply pointed his aircraft at the target and fired. Hit probability increased substantially, particularly against maneuvering targets. Reliability data proved most troubling. The captured aircraft had flown dozens of test flights without significant mechanical failures. Engine operation proved consistent. Turbo superchargers functioned reliably across the entire performance envelope. Control systems worked without adjustment. This reliability stood in stark contrast to German twin-engine fighters that required constant maintenance and suffered chronic component failures. Manufacturing quality analysis revealed construction techniques that enabled mass production while maintaining high standards. Flush riveting reduced drag and simplified assembly. Interchangeable components meant no custom fitting required. Tolerances, while looser than German precision standards, proved functionally superior by reducing binding and friction in operating mechanisms. The reports concluded that American industrial capacity and technological maturity exceeded German capabilities by margins that couldn't be overcome through tactical innovation or pilot skill alone. The P-38 represented not just a superior aircraft design but an entirely superior industrial system that could produce reliable, effective weapons at scales Germany couldn't match. These assessments circulated to senior Luftwaffe leadership, including Galland, to Reich Air Ministry officials, including Reichsmarschall Göring, and to armaments, ministry personnel under Albert Speer. The response proved typically German. Acknowledge the problem, order development of countermeasures, then watch as industrial reality prevented implementation of proposed solutions. Proposals emerged for German turbo-supercharged fighters. The Blome and Voss BV-155, designed specifically for extreme high-altitude interception, incorporated a turbo-supercharged Daimler-Benz engine. Development continued through 1944, but production never commenced before war's end. Even if the design had reached operational status, manufacturing capacity couldn't have supported meaningful numbers. The Dornier Du 335 push-pull fighter represented another attempt at achieving P-38 level performance through unconventional design. Twin engines, one in the nose, one in the tail, drove contra-rotating propellers through a complex driveshaft arrangement. The configuration promised excellent performance with minimal drag. Prototypes flew impressively, reaching speeds exceeding 450 miles per hour. But development delays, manufacturing complexity, and materials shortages prevented meaningful production. By the time a handful reached operational units in early 1945, Allied air superiority rendered any German fighter increasingly irrelevant, regardless of performance. The fundamental problem remained unsolvable. Germany couldn't develop, produce, and field weapons systems matching American technological sophistication while simultaneously fighting a losing war on multiple fronts against enemies with superior industrial capacity. The captured P-38 at Rechlin proved this beyond any reasonable doubt. By mid-1944, the performance gap between American and German aviation had widened to levels that tactical skill couldn't overcome. American fighters, P-38s, P-47s, and especially P-51, Mustangs operated over Germany with near impunity. German fighter production struggled to replace losses while fuel shortages grounded aircraft that did reach operational units. The P-38's role evolved as the war progressed. In Europe, the type transitioned increasingly to fighter-bomber missions, using its heavy payload capacity and accurate bombing to strike ground targets. The arrival of P-51 Mustangs, with even longer range and better high-altitude performance, pushed Lightnings into tactical rather than strategic escort roles. But in the Pacific theater, the P-38 remained supreme. Its range proved essential for operations across vast ocean distances. Its reliability saved pilots when battle damage or mechanical problems disabled one engine. The remaining engine could bring them home across hundreds of miles of open water. Its firepower devastated lightly armored Japanese aircraft. Richard Bong and Thomas Maguire, America's top two fighter aces with 40 and 38 victories respectively, both flew P-38s exclusively. Their success demonstrated what properly trained pilots could achieve with the Lightning's capabilities. Both exploited altitude advantage, concentrated firepower, and energy tactics that maximized the aircraft's strengths while avoiding its weaknesses. Japanese pilots learned to fear the distinctive twin-boom silhouette. The sound of P-38 engines became associated with devastating attacks that Japanese fighters couldn't prevent. Jiro Horikoshi, designer of the legendary Zero fighter, wrote that the peculiar sound of the P-38's twin engines became both familiar and hated by the Japanese all across the South Pacific. German use of captured Allied aircraft through special unit, Kampfgeschwader 200, included attempts to obtain P-38s for evaluation and deception operations. Few fell into German hands intact. The aircraft's ruggedness meant most combat losses involved catastrophic structural failure rather than forced landings. The handful that reached German testing facilities underwent the same thorough evaluation as the Lightning captured in Sardinia. Each examination reached identical conclusions. The P-38 represented American technological and industrial superiority Germany couldn't match. The turbo-supercharger system remained the critical advantage, reliable high-altitude power that German engines couldn't achieve. Every other aspect of the design reflected mature engineering and manufacturing capability that the German wartime industry no longer possessed. The story of the captured P-38 Lightning, tested at Rechlin and flown briefly in Italian service, represents one of the great industrial disparities of World War II. German engineers, working within an industrial system that prioritized theoretical sophistication over practical reliability, produced twin-engine fighters that looked impressive on paper but failed in sustained combat operations. American engineers, applying decades of automotive and aviation manufacturing experience to military requirements, produced aircraft that lacked theoretical sophistication in many areas but worked reliably under conditions that defeated German equipment. In aerial warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. The P-38 Lightning functioned. It climbed to altitudes where German fighters couldn't follow effectively. It escorted bombers across distances German fighters couldn't match. It delivered concentrated firepower with accuracy German wing-mounted arrangements couldn't achieve. Most critically, it did all this reliably, day after day, across thousands of sorties in every combat theatre. German twin-engine fighters, by contrast, struggled with chronic reliability problems, limited altitude performance, inadequate range, and manufacturing quality that degraded continuously as the war progressed. The Bf 1-10, obsolete by 1940 but forced to soldier on through war's end, represented German inability to field effective replacements. The Me 4-10, finally achieving acceptable flight characteristics by 1944, arrived too late and in insufficient numbers to impact outcomes. Post-war analysis by American and British intelligence organizations confirmed what German testing at Rechlin had revealed. Systematic examination of captured German aircraft found mechanical design flaws, manufacturing shortcuts, and quality degradation that reflected industrial collapse. The obsession with individual aircraft superiority and impressive specifications had blinded German leadership to the critical importance of reliability, maintainability, and industrial sustainability. The lessons learned through Rechlin testing directly influenced post-war German aviation development. When the Federal Republic of Germany began developing the Leopard 1 main battle tank and other military equipment in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American engineering principles, the same principles that made the P-38 successful, and deliberately applied them to military vehicle development. The Northrop F-89 Scorpion, developed in the late 1940s as the first jet-powered all-weather interceptor, borrowed conceptual elements from the P-38's twin-boom configuration. While entirely different aerodynamically, The design showed that Lockheed's unconventional approach had proven viable and worth exploring with jet propulsion. The captured P-38 Lightning at Rechlin, with its turbo-superchargers providing reliable high-altitude performance and its systems functioning consistently under test conditions, represented tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical sophistication pursued without regard to manufacturing reality. German aviation designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American aviation designers built reliable aircraft because they understood through hard experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between the P-38 Lightning and German twin-engine fighters influenced not just tactical aerial warfare, but fundamentally shaped broader understanding of military-industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. But Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons systems that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities, while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, perfectly exemplified by P-38 Lightning design and production, proved far more effective than German technical sophistication applied to limited production. The United States produced over 10,000 P-38 fighters of all models, more than Germany's total production of Bf-1-10, Me-2-10, and Me-4-10 twin-engine fighters combined. American industry simultaneously produced enormous quantities of every other weapon type, supplied allies lend-lease, and maintained the highest standard of living among all combatant nations. This economic performance, impossible for Germany to match even before strategic bombing intensified, decided the war's outcome as certainly as any battle. The mathematics proved simple and brutally clear when examined objectively. A P-38 Lightning that reliably reached the battlefield and fought effectively was infinitely more valuable than a theoretical German superfighter that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. An fighter squadron with 80% of its aircraft operational could execute missions that a squadron with 40% operational aircraft simply couldn't attempt. Reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether aviation units could execute their assigned missions. German twin-engine fighters consistently failed this fundamental test throughout the war. American Lightnings consistently passed it. Rechlin testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying aircraft that looked fearsome and possessed impressive specifications, but couldn't be relied upon to function when needed most. The P-38 Lightning didn't win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Rechlin understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached the correct conclusions about American advantages, but understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive and aviation sectors over decades of commercial competition, and simply extended those mature principles to military production with remarkable success. The captured Lightning, that single aircraft that landed at Capo Terra through navigation error in June 1943, told the entire story through its mechanical reliability and consistent performance. Every hour it flew without failure was evidence that German aviation design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test that demonstrated American turbo-supercharger excellence was proof that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Lightning and German twin-engine fighter capabilities proved that Americans had solved problems German engineers didn't realize they needed to solve. The aircraft itself was unremarkable in many ways, just one of over 10,000 produced. What it represented was devastating to German confidence, proof that Germany had already lost the industrial war even as fighting continued, and that American productive capacity could not be matched regardless of German technical sophistication or tactical skill. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.